In this video, we're going to continue looking at applications of exponential functions by looking at exponential growth and decay. So if we have a function, f of x equals pa to the x, that is our general form of exponential functions in general, pa to the x. Okay, f of x is the amount of whatever it is you're talking about at time x. P is the initial amount. And A is the factor by which the quantity changes. It's not the rate. The rate is not actually there. The rate actually would be R would be the rate, and A actually could be thought of in exponential growth. It's 1 plus R, where R is the rate of growth. So if you have a 3% growth, R is 0.03 and A is 1.03. Another way you could actually write this function is f of x equals P and then 1 plus R to the x power. Those are equivalent, actually. So let's look at a couple examples of exponential growth. The world population in 1950 was approximately 2.5 billion people and has been increasing by approximately 1.85% per year. Write a function that gives the world population in year x where 0 corresponds to 1950. So in order to do this, I need P, my initial amount, which I know is 2.5 billion. I need A, which I know is 1 plus R, which is 1 plus the rate is 1.85%. So we got to change that to a decimal and move that back. So 1.0185, or A is 1.0185 then. And so my function would be f of x equals 2.5 times 1.0185 to the x power, and x of course is in years. Now the experts tell us that in 2017 we had 7.6 billion people in the world. Let's see if this makes an accurate prediction for that for 2017. So 2017 minus 1950 is 67 years. So I'd be finding f of 67 to the 67th power, and then that turns out to be about 8.5 billion actually. Let's look and we'll show you. So if we do 2.5 times 1.0185 to the 67th power, 8.53 billion. So they would estimate that there's 8.53 billion people in the world. So it's a lot bit off, I guess. It's off by about a billion. And that usually happens when you have functions used to predict. The farther away you go from where you started, the less accurate they tend to be. Alright, so like another example. At the beginning of an experiment, a culture contains 1,000 bacteria. 5 hours later, there are 7,600 bacteria. Assuming the bacteria grow exponentially, how many bacteria will there be after 24 hours? Okay. Well, we have an initial amount P. We don't have a growth rate, and we don't have an A right now, but we need to write a function f of x equals P times A to the x, and then we're going to find in the end f of 24 is what they're asking us to find. So P we've got, it's 1,000. A, but we do know something. We know that 5 hours later there are 7,600. So we know that 67, when this is 7,600, when x is 5. So I can plug that in, and now this is something I can solve. I can solve for A by dividing by 1,000. and then I'd get 7.6 equals a to the 5th power take the fifth root of a, the fifth root of both sides, so I can get a by itself. So I can go to math, number 5, and I can type in, I don't want answer, I want the fifth root of 7.6, 1.5002. So 1.5002 is a. So my complete function then is f of x equals 1000 times 1.5002 to the x power. Now I can plug in 24 to that function and see what I get. So it'll be 1000 times 1.5002 to the 24th power, and that gives me well over, it looks like 17,381,000. 17,381,000, and it was about 145, and of course we don't use the decimal because they're living things. They don't have 0.6 or whatever of, and that's how many bacteria at that growth rate after 24 hours. Okay. That's a couple examples of exponential growth. Now let's look at an example of exponential decay, which is very similar. It's still the same formula, PA to the x. Okay. F of x is the amount at time x, just like with exponential growth. P is the initial amount, again just like exponential growth, and A is the factor, just like exponential growth. This time A is 1 minus the rate. We never use the rate itself. Whether we're doing growth or decay, we don't use the rate itself. We always do 1 plus the rate for growth and 1 minus the rate for decay, because we're really interested in the amount left. Usually the rate they give us is the amount that they're leaving by, that's the rate of decay, and that doesn't help us. Right, so this is the spot right here with this 1 minus r. That's where kids mostly get this wrong. Alright, so let's look at an example. Filtering. When water is filtered through a layer of charcoal and other purifying agents, 30% of the chemical impurities in the water are removed. If the water is filtered through a second layer, 30% more are removed. How many layers are needed to ensure that 95% of the impurities are removed from the water? Okay, so we want to figure out if 95% are removed, that means 5% remain. We're interested in what remains. We're usually interested. And if 30%, which is 0.3, A is going to be 1 minus 0.3, which is 0.7, because if 30% are being removed, 70% remain. So now for P, we're just going to use 1. They didn't give us an amount, we can just use 1. We can always change it later on if we wanted to. But if there is no P, we're just going to use 1. So I would have A equals 1 times 0.7 to the x power. Well, I know that I want 5% to remain, so that's 0.05. That's going to be A. That's the amount I want left, 0.05. So 0.05 equals 0.7 to the x power. And then we solve that by graphing. And we're going to go into here and we're going to graph this. And it's going to be 0.05 and 0.7 to the x power. And I'm going to change my window here. I'm going to go from 0 to 1 because 0.05 is pretty small. And then I'm going to go, or for my y max, y min and y max, I'm going to go 0 to 1. And then I'm going to go from 0 to 10 here on the x. And let's see. Let's see if they intersect here, and sure enough they do. So that intersection point is our answer that we want. That's x. It tells us how many layers we need. Second trace, number 5 for intersect. First curve, just hit enter. Second curve, hit enter. And guess. You can get it close to that. You don't actually have to because there's only one intersection point. But hit enter. And at 8.3, 8.4. So let's do 8.4. Okay. So 9 layers. Because we can't have 8 layers. 8 layers wouldn't be enough. We're not going to have 8.4 layers. That doesn't make any sense. So 9 layers would be needed to get there. Our last example here, radioactive decay. And radioactive decay is the amount of a radioactive substance that remains is given by f of x equals p and then 0.5, 1/2 to the x divided by h power. P, of course, is the initial amount again. H is the half-life. And x is the time. Okay, it could be years, could be milliseconds. It all depends on the half-life. The half-life is 2 milliseconds, then time has to be in milliseconds. If half-life's in years, then time has to be in years. Okay, so when a living organism dies, its carbon-14 decays exponentially. Every living thing, we have carbon. We're carbon-based beings, but we have carbon-14, which is radioactive, and it decays over time. An archaeologist determines that the skeleton of a mastodon has lost 64% of its carbon-14. The half-life of carbon-14 is 5,730 years. Estimate how long ago the mastodon died. Well, first of all, it lost 64%. So that means 1 minus 0.64, it still has 36% or 0.36. So that is, and our P, since they didn't give us 1, we're just going to use 1. P is just going to be 1. So then what I'm going to have, I'm going to plug into this formula, it'll be 0.36 equals 1 times 0.5 to the x divided by 5,730. And again, for us, for right now, we need to graph that in order to solve. So that's what we're going to do. We're going to go here, go back into y equals, and change this to 0.36, and change this to 0.5 to the x divided by 5,730. And then we're going to graph again. And I doubt they're going to be even close here. Yeah, they're not even close. So let's make this window a lot bigger. It's going to have to be a lot bigger. Let's go from 0 to about 5,000. It looks like it's getting there. It's not there, so let's go change our window again, 5,000. Let's just go to 10,000. Because it looks like it's going to intersect sometime, so let's see it. All we got to do is be able to see the intersection and we'll be happy. And there it is. Well, the intersection is the solution. So we go second, calc, number 5, first curve, second curve, and there's only one intersection on the screen, so just hit enter. So 8,445.62. So x equals 8,445.62 years. So it would have taken 8,000 years. So we figure this mastodon died about 8,500 years ago.